Hello everybody, welcome to Shaders Monthly. Today we talk about importance sampling. Importance sampling is an essential tool in computer graphics. As a first example, we discuss today how importance sampling can be used for real-time image-based lighting if the material is Lambertian diffuse. In the next episode, we will extend this model to perform image-based lighting for the specular part of the microfacet BRDF. We start from the rendering equation, which we have introduced and discussed in detail in episode number 4. The rendering equation calculates the outgoing radiance LO in the direction V for a surface patch at location X with normal N. The outgoing radiance is the sum of two terms. The first term is the emitted radiance LE in the direction V. This term is only larger than 0 if the surface is a light source. The second term is the integral over the complete solid angle of the hemisphere above the surface. We integrate over the contributions from all incoming radiances Li from the hemisphere above the surface patch. Each incoming radiance Li from direction L generates an irradiance contribution dE. Each infinitesimal irradiance contribution dE is multiplied by the BRDF, which is short for bidirectional reflection distribution function. The BRDF defines how much radiance is emitted by the surface patch in direction V if it receives an irradiance contribution from direction L. This way, the BRDF describes the material properties of the surface patch. Okay, for image-based lighting, the incoming radiances Li are stored in a 2D environment image. This image is mapped on a sphere, a dome, or a cube that surrounds the scene. We use a spherical environment map here. In any case, the image provides us with incoming radiances Li from all directions. This means we need to solve this integral from the rendering equation. We have to integrate over all incoming radiances Li from the hemisphere above the surface patch to compute the outgoing radiance Lo. Let's see how importance sampling can help us here. Let's assume we want to integrate a given function f of x on an interval from a to b with respect to x. F of x is typically not given as an analytic function, but it is possible to take samples from the function, which is often the case in rendering. In school, we all learned that the integral is equivalent to the area under the function f of x. Therefore, one way to approximate the integral is to take samples with a regular step size within the interval from a to b and compute the sum of the area of the shown green rectangles. This approach is called the Riemann sum. If we subdivide the interval from a to b into capital N rectangles, the width of a rectangle is b minus a divided by n. And the height is the value of the function f of xn at the current location xn. To compute the area of each rectangle, we multiply its width by its height. We get f of xn times b minus a divided by capital N for the area of each rectangle. Now we take the sum over all rectangles to approximate the integral. Another approach to approximate an integral is called Monte Carlo integration. Instead of using a regular step size, Monte Carlo integration takes samples at random locations. Furthermore, Monte Carlo integration can be combined with importance sampling, which allows us to generate samples with an arbitrary probability density function p of x in the interval from a to b. This is the formula for importance sampling. We see that we sum up the samples at location xn, and each sample value f of xn is weighted by the factor 1 divided by capital N times the probability density function at location xn. Consequently, when we visualize the contribution to the integral of each sample using green rectangles as before, the width of a rectangle is 1 divided by capital N times the probability density function. This means the width is no longer the same for all rectangles, but inversely proportional to the value of the probability density function at the current location. A feature of importance sampling is that it works for any probability density function p of x. Of course, this means we can also choose a simple uniform distribution in the interval from a to b if we want. The probability density function of a uniform distribution in the interval from a to b is 1 divided by b minus a. If we put this into the importance sampling equation, we see that for a uniform distribution the formula looks exactly the same as for the Riemann sum. However, now it is evaluated at random locations and not at regular steps. Using the Monte Carlo integration and importance sampling, we can approximate any integral by a sum, where p of x is some arbitrary probability density function called PDF for short. The PDF must fulfill the condition that the integral from a to b of p of x dx is equal to 1. When we approximate the integral by sampling and we sum up the contributions, as denoted here, this gives us an unbiased estimator. This means we converge towards the correct solution when the number of samples, capital N, gets large. Now, the theory of importance sampling states that the best PDF, which is the one for which the estimator has the smallest variance, would be p of x equals f of x divided by the integral from a to b f of x dx. We have to divide by the integral because we must fulfill the normalization to 1 condition from here. However, in practice, we cannot divide by the integral because evaluating this integral is the original problem that we are trying to solve. Nevertheless, this theoretical result tells us that the chosen PDF should follow the shape of the function as closely as possible. This means that the sampling density should be high if the function values are high, and the sampling density should be low if the function values are low. If we apply importance sampling, this reduces the variance of the estimator and we get less noise in our renderings. But how can we generate sampling positions according to a chosen PDF? One popular solution is inverse transform sampling. Many programming languages provide ready-made functions to generate uniformly distributed samples. With inverse transform sampling, it is possible to transform uniformly generated random numbers into random numbers with other PDFs. To this end, we need to follow the shown 4 steps. Step 1. Compute the cumulative distribution function, CDF for short, from the probability density function, PDF for short. By definition, the CDF capital P of x is computed by the integral of the PDF from -infinity to x. Step 2. Compute the inverse of the CDF. Step 3. Generate uniformly distributed random values u in the interval from 0 to 1. Step 4. Compute random numbers x according to p of x using the inverse of the CDF. Here's an example. The task is to generate random numbers with the PDF c times sine of x, where x is in the interval from 0 to pi. C is a constant that we need to compute from the constraint that the integral over the entire domain of the PDF must be 1. If we solve this analytic integral, it follows that the constant c must be equal to 1/2. Here you see a plot of the resulting PDF. The CDF is calculated by solving this integral from 0 to x, and we get 1/2 times 1 minus cosine x. Consequently, the inverse CDF is r cosine of 1 minus 2u. If u has a uniform distribution, x equals r cosine of 1 minus 2u has a PDF that is equal to 1/2 times sine of x. Let's try out if this works as expected. Here you see the inverse of the CDF, r cosine of 1 minus 2u. Down here we sample the variable u uniformly in the interval from 0 to 1. Then the inverse CDF is applied and we get samples in the x domain. The probability density functions p of u and p of x are visualized by capturing the 2 histograms of the observed sample locations. Let's speed up the sampling process. Excellent, the samples in the x domain have the desired PDF. To get some intuition on why this works, let's look again at the plots of the PDF and the CDF. If the value of the PDF is high, the gradient of the CDF is high. And if the PDF is low, the gradient of the CDF is low. Obviously, for the inverse of the CDF, this relation is reversed. If the PDF is high, the gradient of the inverse CDF is low. And if the PDF is low, the gradient of the inverse CDF is high. This is exactly the relationship that we need, because when the gradient is low, a specific interval in the U-domain with uniform density is mapped to a smaller range in the X-domain. So we get higher densities at those locations. If the gradient of the inverse CDF is high, an interval of the same size in the U-domain is mapped to a wider range in the X-domain and the resulting densities are smaller here. Now back to the rendering equation. As we have discussed in episode number 4, the BRDF of a Lambertian diffuse surface is given by the surface albedo ρd in the range from 0 to 1 divided by pi. If we insert this BRDF into the rendering equation, we see that the BRDF does not depend on the direction of the incoming light, so it can be moved outside of the integral. The variable of integration is the solid angle omega, which is difficult to parameterize. Therefore, we represent the solid angle in spherical coordinates as we have discussed in episode number 4. These spherical coordinates are the polar angle theta and the azimuthal angle phi. Now we see in the figure that the size of a d phi step depends on theta. When theta equals 0, the contribution is 0, and for theta equal to 90 degrees, the contribution is a full d phi step. We must take this into account and use the factor sine theta to scale the d phi step accordingly. This is the resulting double integral of the two variables theta and phi. As we need to integrate over the hemisphere, theta goes from 0 to pi over 2, and phi goes from 0 to 2 pi. Now we apply importance sampling to solve this integral. The integrand f of theta and phi is Li times cosine theta times sine theta. Now we approximate the integral with the importance sampling sum. We put in the integrand f of theta and phi, and now we can freely choose our PDF. We know that the PDF should follow the function as closely as possible. So actually, it would be a good idea to follow the incoming radiance function Li. But Li is not an analytic function and we want to keep it simple here. So we choose our PDF to be a constant c times cosine theta times sine theta. We can determine the constant c by the constraint that the integral over the entire domain of the PDF must be 1. We notice that the integrand does not depend on phi, so we can pull out the integral over phi. Then we solve these two analytic integrals and see that our constant c must be 1 over pi. Consequently, our PDF is 1 over pi times cosine theta times sine theta. Now p of theta and phi is the joint distribution of theta and phi. But we see here that in our special case the joint distribution is only a function of theta and does not depend on phi. For independent random variables, the joint distribution is the product of the marginal distributions, which is a basic rule from probability theory. As the joint distribution does not depend on phi, we sample phi uniformly. This means we do not need to apply inverse transform sampling for phi. For the hemisphere, phi goes from 0 to 2 pi. Thus, the marginal distribution of phi is given by 1 over 2 pi because it is a simple uniform distribution. Now we can solve this equation for the marginal distribution p of theta. The result is 2 cosine theta times sine theta. Next, we want to apply inverse transform sampling for theta. We compute the CDF and the result of the integral is sine squared of theta. Consequently, the inverse CDF is the arcsine of square root of u. Now we are putting it all together. This is the problem that we want to solve. The integral is approximated by importance sampling, which gives us this sum. We put in our selected PDF, 1 over pi, cosine theta times sine theta. These terms all cancel each other out. And we arrive at this very simple formula, where the incoming light direction L is sampled over the hemisphere above the surface normal with theta n equals arcsine square root of un and phi n equals 2 pi vn, and un and vn are uniformly distributed random values in the interval from 0 to 1. For real-time rendering, it is typically too slow to perform importance sampling at runtime. Instead, we pre-compute the integral over the hemisphere using importance sampling and store the result at the location of the surface normal n in a new texture image, which we call pre-filtered environment map. To perform importance sampling, we span a 3D coordinate frame for which the surface normal is the z-axis, and evaluate the integral over the hemisphere with our random theta and phi values from the previous slide. In the case of a Lambertian diffuse BRDF, the outgoing radiance does not depend on the view direction v. Therefore, to compute the outgoing radiance LO, we can simply use the value that is stored at the surface normal location in the pre-filtered environment map and multiply with the surface albedo ρd. So we are going to write two OpenGL GLSL shaders now. The first shader computes the pre-filtered environment map. The second shader performs the image-based lighting of a mesh with a Lambertian diffuse BRDF. It reads the value from the pre-filtered environment map at the location of the surface normal and multiplies it with the surface albedo ρd. To create these two shaders, I use the GSN Composer at gsn-lib.org as a shader editor. The GSN Composer is a web-based tool that I created especially for teaching shader programming. But you can use any other shader editor as well. We are writing pure OpenGL GLSL code, which you can use everywhere. Links to examples that execute the same shader code using C++ or Java can be found in the video description. The implementation of the first shader starts with our example from episode number 5, in which we have applied a texture to a triangle. Click Project and type in the project name Shaders Monthly 05 and click Open Existing. Then open the graph Texture Triangle and press play in the time control panel. Let's replace the triangle with a quad. Click on Create and navigate to 3D, Compute, Generate, Plane. Then we connect the Mesh Data node to the Mesh Input slot of the Shader node. Perfect, we are rendering a quad that exactly fits the size of the frame buffer. The currently applied texture is this image here. We replace it with an HDR environment map image. To this end, we close the kernel project and create a new one. Type the project name Shaders Monthly 10 and click on Create New. Now we can upload an image by pressing Upload Resources. Press Select Files. We select this HDR image. The links to the public domain images that I use in this video can be found in the video description. Once the image is uploaded, we can press Insert here. Now we connect the new image with the My Texture slot of the shader. Next, we set the size of the shader output to 1024 by 512 to match the aspect ratio of the input image. Let's have a look at the shader code. We select the shader node and click the Edit Code button. This dialog is a shader editor of the GSN Composer. In the top section we can define the vertex shader and in the bottom section the fragment shader. Here we have the uniform variable sampler2d myTexture that represents the input texture. In the fragment shader we use the built-in GLSL texture function to get a color value from the texture. The first parameter is the sampler2d variable and the second parameter is the current texture coordinate. The next line writes the texture color to the frame buffer pixel. We are rendering a full-screen quad and the texture coordinates are in the range from 0 to 1. We can visualize the texture coordinates of the quad by setting the outColor variable to vec4 interpolated textchord.s, interpolated textchord.t, 0.0, 1.0. As you see, the red channel goes from 0 to 1 in the x direction and the green channel goes from 0 to 1 in the y direction. Because our texture coordinates are in the range from 0 to 1 and we are rendering a full screen quad, we get a copy of the input texture as the output of our shader. Next, we will replace vec4 textColor equals texture with our own function vec3 textColor equals prefiltered env-map diffuse. We set outColor.rgb to textColor here and the alpha channel to 1. We define the function vec3 prefiltered env-map diffuse in sampler2d env-map sampler in vec2 text. To convert the texture coordinates to pixels, we add the function t2p that we have used before. Now the current pixel in x direction can be computed by float px equals t2p text.x width, and the current pixel in y direction by float py equals t2p text.y height. Furthermore, we need to define uniform int width, uniform int height to get the width and height of the frame buffer. Now we can use px and py as seeds for a random number generator. vec3 random equals random pcg3d uvec3 px py 0. We know this random number generator from episode number 8. I copy the code into our shader. We see that this function is expecting a uvec3 as input, which is a vector of 3 unsigned integers. The output is a vec3, a vector of 3 floating point values. This means that we get 3 random numbers from one function call. These output numbers have a uniform distribution in the interval from 0 to 1. Return random. Apply code. Perfect, we see that we get a different random value for each output pixel. The next task is to compute the surface normal that corresponds to each output pixel. To this end, we create a new helper function that we call vec3 spherical env-map to direction vec2 text. To compute the normal direction, we first have to map the texture coordinates of the environment map to spherical coordinates. When the t-coordinate of the texture goes from 0 to 1, the polar angle theta goes from pi to 0. Consequently, the mapping is pi times 1 minus t. For the azimuthal angle phi, the choice of the origin is a matter of taste. I have chosen the origin of phi to be in the center of the image. When the s-coordinate goes from 0 to 0.5 to 1, phi goes from pi to 0 to minus pi. Therefore, the mapping is 2 pi times 0.5 minus s. Next, we need to map the spherical coordinates theta and phi to Cartesian coordinates x, y, z. Here we have a point P on a unit sphere with radius 1. Consequently, the vector from the center of the sphere to P has a length of 1. Now we first look at the plane that is spanned by the z-axis and the vector to point P. Within that 2D plane, the angle phi has no influence. When the vector to point P has length 1, this line segment has a length cosine theta, and this line segment has a length sine theta. Next, we consider the xy plane. If this segment has a length of sine theta, the red segment has a length of sine theta times cosine phi. The green line segment has a length of sine theta times sine phi. The length of the red, green and blue line segments correspond to the x, y and z coordinates of the point P. This gives us this equation for the Cartesian coordinates. Now, translating this to GLSL code gives float theta equals pi times 1.0 minus text.t. Float phi equals 2.0 times pi times 0.5 minus text.s. Return vec3 sine theta times cosine phi, sine theta times sine phi, cosine theta. Computing the direction of the normal is now simply vec3 normal equals spherical env-map to direction tex. Later we also need the exact inverse function, direction to spherical env-map. It computes the inverse mapping. It takes a direction as input and outputs the texture coordinates for the environment map. As mentioned before, to perform importance sampling, we need to span a 3D coordinate frame for which the surface normal is the z-axis. We define a function, met3 get normal frame in vec3 normal. Now we take some vector, vec3 sumvec equals vec3 1 0 0, and compute the cross product with the input normal. This gives us a vector that is perpendicular to the normal. Tangent equals normalize cross sumvec normal. A cross product of the input normal with this tangent results in a vector that is perpendicular to both vectors. Vec3 bitangent equals cross normal tangent. Now we have three vectors, the tangent, the bitangent and the normal that span the local coordinate system with the normal as the z-axis. In episode number 3 we learned that if we want to build a rotation matrix which transforms a point from a local coordinate system into the world coordinate system, we have to use the three basis vectors as columns in the rotation matrix. Return met3 tangent bitangent normal. Excellent. Now there might be one problem here. What happens when the input normal and the vector that we have chosen here are parallel? In this case, the cross product returns a zero vector and we need to prevent this. Therefore, we compute the scalar product float dd equals dot sumvec normal. For parallel unit vectors, the dot product is 1 or minus 1. So if 1 minus absolute value of dd is larger than some small value, we can use the cross product. In the other case, we know now that our input normal is parallel to vec3 1 0 0, and we can simply select vec3 0 1 0 as a perpendicular vector. Vec3 tangent equals vec3 0 1 0. Met3 normal transform equals get normal frame normal. Okay, let's perform the sampling. For u int n equals 0, n smaller than capital N, n++. We put the loop counter n as the third parameter into the random function. This way we get a different random value for each iteration of the for loop. U int capital N equals U int samples, and samples is a uniform variable. Uniform int samples, description, number of samples. Default value equals 256. Now we sample phi and theta using importance sampling. Float phi equals 2.0 times pi times random.x. Float theta equals arcsine square root random.y. We convert phi and theta to Cartesian coordinates. Vec3 pos local equals vec3 sine theta times cosine phi, sine theta times sine phi, cosine theta. This is the sample position within the local coordinate system of the normal. We need to transform it into world space. Vec3 pos world equals normal transform times pos local. We determine the location of the sample position in world space in the environment map. Vec2 uv equals direction to spherical env-map pos world. We read the radiance value at this location. Vec3 radiance equals texture LOD env-map sampler uv mipmaplevel.rgb, where mipmaplevel is a uniform variable. Uniform float mipmaplevel, description mipmaplevel, default value 0.0. we need to compute the sum of all radiance values Li. Vec3 result equals Vec3 0.0. Result plus equal radiance. Result equals result divided by float capital N. Return result. Our shader generates a very blurry version of the input image. This makes sense because we are integrating over all input radiances from the hemisphere. This means if this image represents a complete sphere, a region of half the image size is used by each output pixel when we integrate over the hemisphere. But we have to be careful here because we assume in the code that we read radiance values from the image. When the GSN Composer loads images from files, they are decoded to the sRGB color space because this is the expected output for our standard monitors. As discussed in episode number 4, we need to perform gamma correction to convert the values from sRGB to radiometric linear sRGB values. We will perform this gamma correction outside of the shader such that the bitmaps for the image are also generated in a linear space. We create a new node. Image Processing, Compute, Color, Gamma. We see that the gamma correction changes the output significantly. We can observe a lot of noise that was probably there before but was less visible. One way to reduce the noise is to increase the number of samples. But before we do this, let's reduce the output image size. Integrating over the hemisphere produces a very low frequency output, so we can get away with a much lower image resolution. Let's try 256 × 128. The output is still noisy, but we have reduced the overall computational effort. Now let's increase the number of samples: 512, 1024, 2048, 4096. Increasing the sample size helps a bit, but it does not solve our problem. Why do we observe the noise? If we look at the input image, we see two very bright light sources. One light source is this bluish window and the other one is this street lamp. When the random process of selecting input radiance directions is choosing these bright light sources, we get a very high contribution. Otherwise, the radiances are low. Sometimes we have a hit, sometimes not, and this produces a noise. As I have mentioned before, it would have been a good idea if our importance sampling would follow the incoming radiance function Li. Here we could gain a lot from importance sampling because the incoming radiance function contains high frequencies. But this is more complicated and we need to address this in a future episode of Shaders Monthly. As a quick fix to our problem, we can reduce the high frequencies in the input image by selecting a higher bitmap level. We have discussed bitmaps in episode number 6. When we go up one bitmap level, we reduce the resolution by a factor of 2. We average 4 pixels from the lower level to generate a pixel for the current level. This is a simple low-pass filter. The approach will introduce some errors, but hopefully reduces the noise. This is the result for level 1, 2, 3, 4, 5, 6, 7, 8. Okay, we have to go to level 8 here to get an acceptable noise level. But the locations of the light sources have also moved because the resolution at level 8 is only 4 × 2 pixels if the size of the original image is 1024 × 512 pixels. At a bitmap level of 5, the resolution is 32 × 16, which might be still acceptable in terms of the locality of the incoming light, but the noise is still visible. This means we have to give up here. Our current input image is perfect for showing the problems, but is too difficult for us at the moment. Let's load another environment map that does not have small bright light sources. This looks okay. We save the output image. Image Processing, Compute, File, Save. We set the format to PFM, which is a lossless floating point format. And the file name is Teatro Massimo 1K Pre-Filtered Diffuse. Next, we implement the second shader that performs image-based lighting of the mesh with the Lambertian diffuse BRDF. To this end, we modify our shading example from episode number 9, which uses a microfacet BRDF and a directional light. Click Project and type in the project name Shaders Monthly 09 and click Open Existing. Then open the graph Microfacet BRDF and press play in the time control panel. Then we close this project and open our current project Shaders Monthly 10. We insert the environment image Teatro Massimo 1K and our pre-filtered version Teatro Massimo 1K Pre-Filtered Diffuse. We open the shader editor. Here we compute the irradiance of the directional light and multiply it with the BRDF. We comment out this section and add a note here: Direct Light Computation. Now we add the code for image-based lighting. The surface normal is given by N in this shader. We use the surface normal as the direction that we look up in our pre-filtered ENV map. Vec2 ENV equals direction to spherical ENV map N. And we copy our function direction to spherical ENV map into the shader somewhere. Now we multiply the surface albedo with the value from the pre-filtered environment map. Radiance plus equal base color times texture ENV map diffuse ENVUV.RGB. That's it, very simple, only 2 lines of shader code. And up here we add uniform sampler to D ENV map diffuse min filter equals linear mag filter equals linear. Apply and close. We connect our pre-filtered ENV map with the ENV map diffuse input slot and we get a result. Well, it looks okay, but it's hard to tell if the output is correct. Just for fun, we could connect the original environment image to the ENV map diffuse slot. This looks very specular because the original environment image still contains all the high frequencies. But it is physically wrong. We will talk about how to implement specular reflection in the next episode of Shaders Monthly. But at least we have verified that it makes a difference which environment image we use. Back to our pre-filtered ENV map. To display the environment map in the background, we create a sphere mesh that surrounds the scene and use the image as a texture. As we have covered texture mapping before, the modification of the graph is not very interesting and nothing new, so I fast forward this part. Here is the final result. The diffuse shading of the stone demon matches the environment. Here are some results for different environment maps that I have already presented at the beginning of the video. That's it for today. If you have questions, use the comments or get in contact with me. As always, if you prefer C++ or Java source code, this can be found in the video description. See you at the next episode of Shaders Monthly.